All right, section 5-8 is on definite integrals applied to area and other problems. And the objective, recall, is to write a definite integral as a product of x and y, and then evaluate using the fundamental theorem of calculus. And so you've seen the technique. I want to look at one variation to that technique, depending on the functions, or it might not be functions that you're working with, just the curves that you're working with. So let's take a look at this example here to help illustrate this. The example you saw to start out with and the problems you've done so far have all used what we would call a vertical strip. You drew a strip vertically and labeled the endpoints there as x, y1, and x, y2. Now there are times where it will make sense, instead of using a vertical strip, to make a horizontal strip, and we'll illustrate that here with an example. And with a very slight change to your equations that you're working with, as well as the endpoints that you're working with, it's basically the same problem. So let's take a look at these two, well, it's actually these two curves here. They're not functions, but these two curves. One's a linear function, one is a curve, but definitely is not a function, doesn't pass the vertical line test. And let's look at the difference here between using vertical strips versus horizontal strips. So on the left here, let's use vertical strips. So I'm going to go ahead and sketch in a vertical strip. And remember that the whole idea here of using a vertical strip or using any strip is that you're just drawing in one representative strip. And so if I were to sketch a strip here, it might look something like this right here. And we have one strip there where I start at the curve on the top of that strip, and then I have the line there at the bottom of that strip. And so that one strip there, we could say represents many of the strips in this region. The problem is that one strip doesn't represent all of the strips in this region. This represents all the strips, in fact, that are on the left of the y-axis. If I look over here on the right of the y-axis and drew in a strip, I'd end up with a strip that looks like this, where it goes from the curve on the top to the curve on the bottom. So in other words, if I were to calculate the area of this strip over here on the left, we'd be taking the curve on the top minus the line on the bottom. Versus this one right here, it's the curve on the top minus actually the same curve on the bottom. You can see how those two strips are not representing the same quantity every time. All right, one's curve from the curve to the line, the other one's from the curve to the curve. So for this reason, if I wanted to use vertical strips here, I would have to actually split this up into two separate regions. I could use this technique, but it would require that I actually solve the problem in two steps. I'd have to look at this region over here on the left and calculate its area using the curve and the line for each strip, going from the curve on the top to the line on the bottom. And then I would have to consider this region over here on the right and calculate its area using the curve on the top and the curve on the bottom for the height of each one of those strips. And then, of course, when I add those two regions together, I would get the area of the entire region between the two curves that I have here. So it would require a little bit of extra work to do it using vertical strips. It would require actually, I guess in essence, almost twice the work, because of the fact that you have to set up two separate integrals that you'd have to solve. On the other hand, if we take a look at that same set of curves there, or equations over here on the right, and instead of using a vertical strip, we use a horizontal strip. And let's just say that we draw a horizontal strip that's somewhere about right here. Again, the whole goal is that I draw in one strip that represents all the strips in that region. And now you can see that this one strip does, in fact, represent all the strips in that region, because the right side of this strip is on the curve, and the left side of this strip is on the line. And in order to find, in essence, the height of this strip, I would take the curve on the right minus the line on the left will give me the height of that strip, or I guess it's really maybe the length here if you want to think of it that way. But it's always going to be the curve minus the line to get the height of that thing. And so using horizontal strips here, I would not have to separate this into two separate regions. I would actually get this entire region right here by using this one strip. Every single strip in that region would be represented by the curve on the right side of that strip and the line on the left side of that strip. So here's a good example of why it might be advantageous for us to use horizontal versus vertical strips. Now, one thing to note here, that if you're trying to find the height of the strip there and you're working with vertical strips, that the way that we calculate that height, it's always the top minus the bottom. You want it to be a positive value. So since it's vertical, you take the larger y value, that's on top, minus the smaller y value, that's on the bottom. So it's always the top minus the bottom. On the other hand, if you're using horizontal strips, I still want that length or height, whatever you want to call that, of that strip. I still want that to be a positive value, so I have to take the larger x value in this case, and the larger x value is over on the right, minus the smaller x value, which would be on the left. So in either case, we're always trying to make that length or that height of that strip a positive value. So think about that as you're doing that calculation, that it's top minus bottom because we're making it a larger value minus a smaller value, or if it's horizontal, it's the right side minus the left side because I want that length there to be positive. All right, so let's try an example of actually these two curves here and see if we can integrate this to find that area between those two curves. If you look at example 2, it says for the region in the figure that we just looked at, actually bounded by the graphs of, let's go ahead and write these two equations down here. They give us x is equal to 3 plus 2y minus y squared. And they give us x plus y is equal to negative 1. And it says to write an integral for the area and evaluate it numerically. All right, and evaluate the integral exactly by the fundamental theorem of calculus and compare your answers. All right, they're saying to evaluate it numerically by using a Riemann sum or a trapezoidal sum. I'm going to leave that for you to explore. I'm just going to do use fundamental theorem just so we get a little more practice of evaluating these this way. All right, so let's give ourselves this sketch here again. I know that we were just looking at this sketch, but let's make sure that, oops, I want to have a little more room than that. Let's make sure that we have a sketch here to illustrate exactly what we're trying to do. So we have a curve that looks something like this, and we have a line that crosses at the same point here. I'm going to see if I can sketch that approximately where it's at, somewhere around there. And there's the sketch of these two. Now, they gave us the sketch of these, so that was obviously a little bit easier for us to come up with. One thing you could do to help yourself sketch this, if you, let me just move this down here so I can illustrate with this equation that I have up here. Since this is solve for x, this first equation that they gave you, if you can factor it like we saw before, that sometimes will be helpful in finding, in this case, the y-intercepts. And so I can see that this factors into 3 minus y and 1 plus y, I think it looks like. 3 minus y, yeah, that's what's going to factor into. It gives the positive 2y there in the middle, which that tells me it crosses the y-axis here at 3 and at negative 1 are these two intercepts, which actually I'm going to need to know those here, and or I'm going to need to know at least one of those in just a minute. But the x or y-intercepts in this case will be helpful in sketching it. I know where those 2 points are, and the fact that it's got a negative y squared would tell me that it opens up in the negative x direction, so it opens up to the left. That might be helpful as well. The other equation, of course, you could solve it for either x or y, whichever way you wanted to do it. I would probably say it's easier to solve it for y, and then you could graph that thing. If I solve this thing for y, of course, I get y is equal to negative x minus 1. Okay, but you can solve it either way, obviously. In fact, I'll go ahead and write it both ways just so you can pick which one you want to use. If you solve it for x, you'd have a negative y minus 1. The other way you can do this on your calculator, let me just illustrate this again so you can get these sketches yourself. If you notice there, you have an equation. The first equation is solved for x. So I could, if it was solved for y, I could sketch this thing. If I could swap the x's and y's, I could actually solve this. It'd be y equal, or I could graph this. Y equals 3 plus 2x minus x squared. I could graph that if I swap the x's and y's. Which, of course, when we swap the x's and y's, that's actually the inverse. Okay? And you have a command on your calculator that allows you to sketch inverses. And so that's what I'm going to do. Let me set my window here first of all. And since really this is the only part of the graph I want to see, I think I'll try to set my window so I only see that part of it. So we'll go from negative 6 to 6. I think in both directions will give us a decent window here to work with. And let's go ahead and in y1, let's put in the linear function. That was negative x minus 1. And we can get that to show up actually first. And then if you want the inverse of the graph y equals 3 plus 2x minus x squared to show up under your draw menu, second and then your program button. You have a command under here called draw inv, which will draw the inverse of a function. So if I put in 3 plus 2x, again I'm swapping the x's and the y's here, minus x squared. If I swap the x's and y's and then tell it to draw the inverse of that, that'll give me the graph that I'm looking for, and just press enter. There we go. There's that sketch. Okay, so you can, there's several ways you can come up with this. In fact, you can even use parametric equations to help you do this as well. All right, you pick the way that you want to get the sketch of it, but either way, we're going to get this sketch here, and we want to find the area of that region. All right, that's all kind of a side note. Now let's tackle this problem. Let's again draw in our strip that we need. Let's label the endpoints. Now this time, the x values are going to be different, and the y values are going to be the same. So we'll call this point over here on the left, we'll call that x1y. Oops. x1y. And we'll call this point over here on the right x2y. Again, the x values are different, it's the y values that are the same. And I want to measure this distance, or the thickness, or the height, if you will, or I guess it's the base sometimes we call this, of this strip, this distance right here, vertically in this case. Since it's vertical, it's no longer a change in x. It's no longer a small change in x. It's a small change in y. So we call that distance dy. So we're going to get an equation here in terms of y and dy as opposed to x and dx like we did before. Let's go ahead and calculate the area of that one strip. We'll call it dA. So we'll say dA is equal to, again, think of it as a rectangle. In fact, you could even sketch that as a rectangle. We did that before, if that helps you to see that we're actually thinking of it that way to calculate this. It's the base times the height in essence. So it's the difference in the x values. So again, it's the larger x value over on the right, that's x2, minus the smaller x value, which is over on the left, right minus left, times the thickness, or the base, whatever you want to call that, of that strip. We call that dy here in this case. Now I want to get this all in terms of y, and basically what dictates that for us is this differential right here. You have to look at your differential, and that tells you what variable you need. So the fact that I have dy there tells me I need to change the x1 and x2 over to y values. And fortunately, we have equations where we know exactly what those are. If you look at x2, x2 is over here on the right. It's on the curve. So I need to know what x is equal to as a function of y. And so there we go. It's 3 plus 2y minus y squared. So that's x2. And then replace x1 with what it's equal to. x1's over here on the straight line, so I need to know what x is equal to as a function of y. So that's a good thing, actually, I guess, that we wrote this down, because that's what we need here. X is equal to a negative y minus 1. and that's times dy. All right, and again, let's simplify this. We have to integrate. We might as well make this a function as easy to integrate as possible here for us. So let's put our constant first, I guess, here. We've got 3, and then you get a minus a negative 1, so that's actually 4. We've got 2y minus a negative y, that's going to be 3y, and then minus our y squared times dy. And you could put the, I guess if you wanted to put the quadratic term first and the constant at the end, it doesn't really matter. I just put it that way since the constant was at the beginning to start out with. And now that we have this, we are ready to integrate this thing. So we're ready to integrate dA, and we're ready to integrate this 4 plus 3y minus y squared dy. The only thing we want to do over on the right side is find the limits of integration for us, the upper and the lower bounds. So let's go back up to our sketch. And you want to think about this vertical strip here, or this horizontal strip here, and sliding it as far down as possible. If we slid it all the way down, as far as down as we could, we'd get to this point right here. So the lower bound for this is y equals negative 1. And the key is that it's a y value. Again, look at your differential here. The differential is in terms of y. So that tells me I'm looking for a y value, not an x value. So y equals negative 1 is the lower bound. And then if you think about taking that strip and sliding it all the way up as far as it could go, all the way up past 2, past 3, all the way up, you get all the way over here to this little point right here where these two curves intersect, and that would be the highest point, which we don't know. So again, we've got to do a little bit of work in order to find out what that point is. So it's where the two curves intersect. So let's just set the two curves equal to each other. So you have 3 plus 2y minus y squared is equal to, set that equal to the x equals negative y minus 1, so that's a negative y minus 1. So here we have a quadratic equation, and we got lots of ways you could solve this. You could graph this and find where those two curves intersect, or use your quadratic formula. I'm going to get everything over on one side here for us. So let's move everything to the right, I guess. So we'll end up with a positive y squared. We'll subtract 2y to give us a minus 3y. We'll subtract 3 to get a minus 4. And again, you got several options at this point. Use quadratic formula. You can use solver. I think this factors nicely, so I'm going to go ahead and just factor this thing, but use whatever technique you're comfortable with. So it looks like this factors into y minus 4 and y plus 1. So it looks like y equals negative 1 is one solution, which that's this one down here. That was that one intersection we already found, or we already knew. And the other one is up here actually at 4. So this actually is occurring up here at 4. So those are our limits of integration. The upper bound is 4. All right, let's evaluate this using fundamental theorem now. So on the left side, when we integrate dA, we get A, our area of this region that we're looking for. On the right-hand side, integrating term by term, integral of 4 with respect to y, that's got a dy there, so that's going to be 4y, not 4x, but 4y, plus 3 times 1/2 y squared minus 1/3 y cubed. And we're evaluating that from negative 1 to 4. Now sometimes if this function's pretty nice to work with here, we just simply evaluate it right here and get our result. And this one doesn't look quite as much fun to try to do that with, so I'm going to show you another way that we can do this, and that is to take this equation that we got for the antiderivative and plug that into y1 on our calculator, and then just have it evaluate y1 at 4 and negative 1 and take the difference. That's all we really want to do, so let's do that here on our calculator. I'm just going to get rid of our function. I don't really need that right now, so I'm going to write this as 4x plus 3/2 x squared, and then minus 1/3 x cubed. All right, there is our antiderivative, and let's tell it to take y1 and evaluate it at our upper bound minus y1 evaluated at the lower bound of negative 1. And we end up with 20.83 repeating. which I guess you can write it that way. 20.83 repeating, 833. Remember to put 3 decimal places. Of course, 8.3 repeating there is what, 5/6? So this is actually 20 and 5/6. You can double check that on your calculator there if you want to, or in fact you have a way that you can convert that over to a fraction. If you go to your math menu, math, and then go to this display as fraction button there, you'll write it as 125 over 6, which simplifies down to 20 and 5/6. So you can write it either way. All right, that's the end of our section here.